Greetings all! We are going to present LWISAT mission.
Water is one of the most valuable and threatened resources for life. As recent as 2017, at least 45 countries were in conflict due to water access. This is an adverse situation, as water is needed in various processes and industries. This includes agriculture, a sector that represents 60% of all jobs in Central America and the Caribbean. Thus, it is understandable that one of the Sustainable Development Goals is focused on water. SDG 6 clean water and sanitation targets include implement integrated water resources management at all levels and expand international cooperation to developing countries in water and sanitation related activities. According to the WHO, by adapting to the water effects of climate change, we will protect health and save lives. And by using water more efficiently, we will reduce greenhouse gases. There is a global need to find efficient water management techniques, not only on Earth, but also outside of this planet. A new era of deep space exploration will unravel with ARTEMIS mission, which has the goal of establishing multiplanetary human presence. The Moon is the first step to prepare for the mission to Mars. The ARTEMIS base camp on the surface of the Moon will enable robots and astronauts to explore and conduct more science than ever before. The Gateway in lunar orbit will provide essential support for long-term human return to the lunar surface and serves as a staging point for deep space exploration. In 2020, Stratospheric Observatory for Infrared Astronomy, Sofia, obtained the first quantifiable data on water in a lunar crater. In the late 2000s, there were a series of missions, such as Chandrayaan-1, that discovered hydroxyl on the lunar surface. This caused a sequence of missions such as LCROSS, LRO, Flashlight, and LADEE, whose objective was to search for water. These discoveries led to a search for the answer of the question: how much water is there and where is it located on the Moon? The Lunar Water Index satellite mission targets to identify and quantify water on the Moon poles through a CubeSat constellation featuring spectral measurement instruments. This mission not only encompasses the concept of deep space exploration, but is also focused on improving the quality of terrestrial life. Obtaining water data on the Moon is the beginning for the development of improved water management systems on Earth. This data is important to scientific communities as well as governments, as it provides sustenance to make better choices based on facts. The Moon is our opportunity to anticipate to extreme environments and understand how to find resources within them. LWISAT is the first step for self-sustaining life outside of Earth. The general objective of our mission is to develop a remote sensing water index supplied by a 5 nanosatellite constellation deployed in a lunar orbit. The scientific objectives include acquire the data to generate a lunar water index in order to decrease the cost of exploration and analysis and increase the precision in multiplanetary and mining missions. Deliver a baseline for high-quality spectral Venn diagrams of different potential water deposits located on the Moon. The engineering objectives include validate the correct operation of the optical sensor for replication and usage in future deep space exploration missions. Provide databases to support deep space exploration, research, and enable better decision-making for companies, universities, governments, and space agencies around the world.
The improved water management techniques will be implemented in the developing countries such as those in Central America. It will also serve as an inspiration for the new generations to pursue STEM careers. Central America hasn't had an active participation in aerospace projects. Just in 2018, Costa Rica launched their first satellite, and 2 years later, so did Guatemala. LWISAT seeks to close that gap and thrust space innovation in Central America. To contribute solutions to the problems that are affecting these regions.
After launch from Kennedy Space Center aboard NASA's Space Launch System, the SLS, LWISAT will begin its travel to the deep space. During the translunar injection, the interim cryogenic propulsion stage and the spacecraft adapter will separate from the service and crew modules. As the interim cryogenic propulsion stage is disposed of, it will be directed into heliocentric orbit. LWISAT will take advantage of the approach to the Moon to carry out the deployment of the Constellation.
Our CubeSat constellation is composed of a master-slave architecture in which each one has a specific purpose. The slave satellites will be the ones gathering the data via the optical system and sending it to the master unit, which will process the information and sending it back to us for further analysis. Both configurations of CubeSats will launch different systems that will allow them to fulfill their tasks. The systems can be grouped into electrical power, communication, data handling, attitude determination and control, and protection systems. The systems will be accommodated in a 2-unit structure for the master and a 3-unit structure for the slaves, due to the need to house the optical system. All of the needed components of each system are commercially available, in exception of the optical system.
Now, here you have the possible design or the renders in our future constellation. This one is a 3U. It is going to be used for the slave. And this one is a 2U. It is going to be used for the master. This is because the master doesn't need the scientific experiment inside of it.
LWISAT's constellation is composed of 3 orbital planes, 2 for gathering scientific data and 1 for relaying data and commands. When designing lunar orbits, gravitational perturbations due to Earth's pull and lunar high-density craters have to be taken into account. For this mission, these perturbations are avoided with the usage of a set of circular frozen orbits, specifically the family found at 86 degrees, whose inclination is responsible for maintaining their orbital parameters almost constant throughout the mission and for providing polar coverage. Each scientific or slave orbit holds 2 satellites, each separated by 180 degrees at a low altitude of 163 kilometers. One satellite detects the presence of water and the other quantifies it when it passes over the detected zone. The relay or master orbit holds the master satellite and enables it to communicate with the constellation and with the lunar orbit gateway.
LWISAT mission requires 2 payload systems. Each of them have different scopes and different objectives that will help us achieve the goals mission. There are 4 units of CubeSats that will carry the payloads. 2 of them will have an ultraviolet infrared remote sensing system, and the 2 remaining will have a bathymetric LiDAR satellite system. This system has the objective of detecting water through the index of refraction in the lunar surface, both in the illuminated and non-illuminated parts, and also determining the range of change in the natural light conditions. For this type of hybrid optical measurements, LWISAT needs to supply the technologies for 3 types of scenarios. This next system is capable of quantifying water and ice formations on the lunar surface, in addition to mapping and recognizing the depths of water areas previously detected with the hybrid system, using bathymetric methods built with LiDAR technologies for CubeSat applications. The LiDAR results will be post-processed in order to find the level and topographic environmental conditions using bathymetric requirements such as gravity waves on the water surface can alter the geometry of the laser beam before refraction in the water column. When the laser beam travels in the water column, it undergoes absorption and scattering, causing the laser beam to spread. To process the data and get the water index, we will be using the HiSweep Max software or any other program with the same characteristics, which has the capability of processing the multi-beam, backscatter, or for the interest of the mission LiDAR, the water column. This tool is going to be analyzing the data for the acquisition of the water index. It also allows the creation of 3D party files for a better understanding for the stakeholders.
This is a high-cost space mission, not only because of the goal that it wants to achieve, but also because of its innovation. Due to this goal, it is expected for this constellation to operate for at least 18 months, in order to gather enough data to generate the Lunar Water Index. The cost range for these constellations falls between $50 and $100 million. This mission could be partnered primarily with NASA and supported by JAXA. These two agencies will provide the financing and development of our informatics operating system that will offer access to first-hand and premium data for the quantification and location of the water reserves on the Moon. This will work as an essential point of cooperation for missions such as the Lunar Flashlight mission for the ARTEMIS program.
In conclusion, this mission will gain new knowledge and help alleviate social problems on Earth, especially in the Central American region. In summary, LWISAT mission's goal is to identify and generate a water index from the water resources located on the Moon's surface, in order to contribute to deep space science and exploration research. The technological approach is a CubeSat-based solution. The use of nanosatellites provides a low-cost platform for the mission. The scope of the project involves increasing the precision in multiplanetary and mining missions, as well as the delivery of high-quality spectral band diagrams of different potential water deposits located in the Moon. The generation of these databases will enable better decision-making and provide solutions to water management problems around the world. Future missions can be developed using LWISAT's findings.